Okay, so hello everyone. Welcome to another class. Today is day 5th. So as always, thanks for joining us today. And I hope this class is also helpful and interesting because today we are going to learn how to perform inversions in NLTE with DeSIRe. So what we are going to do is to keep things simple and make it easy to follow all the process. We're going to first create synthetic profiles that we will also add some noise just to make them a bit more realistic. And then we will take those profiles and then we will invert them. So the idea is that when we invert the profiles, we will be able to check the accuracy of the inversion, comparing the profiles we get from DeSIRe with those that we use as an input. But also, as we did the synthesis, we can also compare the atmospheres that we get as an output with those that we use for the synthesis. So this is the complete package. Okay. So then as a miscellaneous, this week we have, and this is that because we have a new version of DeSIRe. So it's from March. So then you can go to the Dropbox folder, and then inside DeSIRe, you will have a folder that is called source code. And there you will have the previous version, because as I said a few classes ago, I would like to keep all the versions just in case you want to do a comparison because something suddenly changed and you want to double check it. But also I will always keep there the newest version that we are using for the course and in general. Okay, so you can download it. Then it's, if you remember, it was very simple to install it. So you just go to the source folder inside DeSIRe and then just type make install, and probably you will use eFortran. So then just add this label and then it will just install and work. Okay. So the idea is that today's folders, the one we will use, I'm already running on this new version. So my recommendation is just create a new folder called DeSIRe and this label, and just copy the new folders from today in that distribution, and then just use this one for the next classes until we have a new update that hopefully it will not be less than a few months. Okay. So then I think that's all for the beginning of the class. So then let's go to DeSIRe. So now, as I said, I'm in 2022, March 3rd. And there we will have 3 folders related to today's class, so related to day 5. So let's start with the first one. Here inside, you have essentially the same files that we used for synthesis in the last class. So we are going to have input files, and then we will have this run.pro that is an ideal script. So let's have it here. Just let me move this a bit. So then the idea is, sorry. So then the idea is we are going to do synthesis. So for that, the first thing we need to do is to create an atmosphere that we will use as an input for the synthesis process. And then, as I said, it's the same one as before. So it's going to be the DeSIRe atmosphere. And we are going to change some of the parameters. In this case, the microturbulence, field strength, line of sight velocity, inclination, and azimuth. Okay. And then we are going to save it with this name because here in the synthesis control file, we are going to call an atmosphere that is called input.mod. And the rest of the things are the same, okay? But also I'm going to save it with a different name because later on we are going to use it for comparing the inversion results with this one. So just to keep things with as organized as possible, I'm going to just label it as a label 1 because we're going to use 2 atmospheres today. And then here, I just make the plot. So let's check it. So it's called atmosphere synthesis 1. So in day 5 in HD figures, you go to run 1. And then it's this one. So just as a reference, is the temperature is the same as the DeSIRe. We have a magnetic field that is reasonably strong. The inclination goes to almost 0 to 50 degrees, and the line of sight velocity is relatively strong, around 4 kilometers in log tau -5. Okay, but it's just linear gradients. So to try to keep things relatively simple for now. And then with that atmosphere, we run DeSIRe. Okay, so as it's the same as before, I'm not going to enter in the details of the grid files and the lines file. So it's the same as the previous class. So we are synthesizing the iron 630, the calcium 8542, and calcium 8542. Sorry, calcium 8498 and calcium 2 8542. And then we added lines in the wings of the calcium lines, photospheric lines in the wings of the chromospheric lines. Okay, so then we read the profile, and then this is something new from this class, and is that I want to add some noise to make things more realistic, because in general, every time you analyze an observation, you have noise. So I'm using this IDL random normal distributed function. So it will add some values scale with an amplitude that I will define later, and they will be randomly distributed. Sorry, normally distributed values. Okay, so then I'm going to add it to Stokes I, Q, U, and B. And in general, I am adding a relatively small value, but I think it's okay for this example, although in general you will have here a larger amplitude. And also I put it a note here because I wanted to have a bit more noise in Stokes I. There's no clear reason for that. It depends on the instrument and on the data reduction. But in general, I usually find that the Stokes I noise is larger than for the Stokes parameters. So the polarization Stokes parameters. It could be flat field, it could be other things. But in general, I found this. So I just, for having some consistency with my experience, I added this noise with a larger amplitude. But the truth is that if you want to really reproduce with high accuracy some instrument behavior, then I recommend you to check with the PIs or people that have used the instrument, just to have an idea of what are the expected noise values for a given integration time and a given configuration. But I think here this is reasonable, and I will just show you the plot. So as I explained in the previous class, we have that when we read the Stokes I vector or the Stokes profiles, we have all the profiles together. So the 630 window, the calcium 8498 window, 9542. So now we are separating it just to make the plot separated in a spectral range. So then the first figure that we are going to make is this one that is here, here. And this is how it looks. So this is the synthetic profile. And as I mentioned, the noise is okay for the Stokes polarization parameters. They are really large in Stokes P, but you can see it in Stokes Q and U. And then as I added a bit larger noise in Stokes I, you can see it also here. And I would say that this is something that you, for example, see in Hinode. So these variations that you hear here, you can see it, for example, in Hinode's P data. So I think it's okay. It's realistic. So we can use it as a reference for this example. Okay. So then we just do the same. We load the calcium 8498 and 8542, and then we make the plots. Okay. So here we have that this is the first atmosphere. Polarization signals Q and U, they are relatively small because the atmosphere, if you remember, it went from almost 0 in the lower part of the atmosphere and then to 50 in the upper part. So it's not very inclined. So then basically the noise we added is what is dominating in the Stokes Q and U. And then you have something Stokes I, but it's okay, it's still reasonable. And it's also now perceptible here because signals are smaller, the amplitude is smaller than in the iron lines because those lines are very, very sensitive to the magnetic field. But there still is something that is not really bad, so it's adequate for this example. Okay, so then now we go to the 8542, and it's the same. So Q and U are essentially noise. Stokes I is relatively noisy. I think it's a bit okay, but I think it's fine. And then the same for Stokes V. In this case, the 8542 line has a large amplitude, so noise is not so important in the central part, but you can see it, for example, in the wings that there are some variations. Okay, so then this is the first part, and now what I'm going to do is to write those profiles that we have synthesized. We added noise, and we checked that was reasonable. So we are saving them with this name because we are going to use it later as an input for the code to perform the inversion. Okay, so far we created an atmosphere. We synthesized Stokes profiles with the same configuration as before. We added noise to those Stokes profiles, and then we save them with the same format that DeSIRe uses. Okay. So now we are going to repeat exactly the same process, but changing the atmosphere, just to have today two cases where the atmosphere are slightly different. So in this case, we are giving different values. I will show you now the plot, but it will be easy to see what we did. But again, we are saving this with a different name also, so we can use it later for comparison purposes. And now we are going to check all the figures that I have in the left folder with the subindex, or with the index 2. Okay, so then this is the atmosphere. Now I put it a much stronger field strength. The velocity was almost 0. I thought it was maybe consistent, and the magnetic inclination is now even more vertical. So something very, very simple, but just wanted to have a very strong field strength just to see how the profiles look like and how the code behaves. Okay, so then 630. Now we have Stokes V are really, really large, and they are broad because probably we are maybe close to, or maybe already in the strong field regime. We have also that the splitting, the Zeeman splitting is now visible in 6302. And now the noise is even here, but I think it's okay. And then Q and U are very small, even for the photospheric lines. And if we go to 8498, we have again very, very strong Stokes V signals. And then photospheric lines are splitted. And Q and U are essentially noise. It's even worse than before. And we can do the same check with the calcium 8542. And again, amplitude of Stokes V is really good, and Q and U are not so good, and Stokes I, it's okay. We don't usually, I think we would not expect to see Zeeman splitting on the calcium lines because they are so broad, and the magnetic field above is not so high. So you can see it in general in photospheric lines, but probably in the chromospheric line is very difficult to detect it. Okay.
Could I ask a quick question? Is it okay?
Hi, yes. Hi, Ryan.
Hi,
how are you?
Yes, I'm good. So could you reopen that figure?
Yes, yes. Sorry.
In that third line from the left, why in Stokes V is the continuum not just 0? Why is it raised next to the line?
So you mean where? Sorry.
So the third line in Stokes V.
Stokes V. This one.
Why is the continuum, if you look to the left and to the right, why is it not? Why does it have that gradient? Yes,
because this is the calcium line. So this part is not continuum yet. So this part, let's assume that we are 8542.5. So 85.4.5 is still the wing of the line. So then this is still the Stokes V contribution of the wing of the line. So the continuum of the calcium 8542 line is already here. So then here is where you see that it's essentially 0, but this part is still the line. So it's a Stokes V profile.
So is it true that if you had a much weaker field that you wouldn't really see that being raised? Does it correlate with the field strength, how raised that is in the wing?
Well, I think it correlates with the field strength in the lower atmosphere. So if you have, because the wings are sensitive to the lower part of the atmosphere, right. So as soon as you have some magnetic field that has some strength in the lower part of the atmosphere, you should see Stokes signals there. I mean, with appropriate orientation. So I mean, vertical field strength like 300, 400 Gauss, you will always see this contribution. If the field strength is complex in a way that there's almost no strength in the lower part of the atmosphere and something in the top, then maybe this will be much weaker. But I think it's essentially that if you have field strength in the lower part, then you will have signals from the wings of the calcium line.
That makes sense. Thank you.
I think
you can basically think of the Stokes V as the first approximation as a derivative of Stokes I times the magnetic field times some constants, right? And so whenever you have a shape in Stokes I, you will see in Stokes V when you have a negligible magnetic field.
Yes.
That makes sense.
Yes. Okay. Yeah. Thanks, Ryan. So can I continue? Any other questions from? No? Okay. Okay. So then just let me go back, and then what I was saying is that we just did the same. So the profiles are reasonable. So we added noise, and then we made the plots to check that everything was realistic. And then we are again saving the profiles, now with a different name, because I wanted to keep things organized. So now we are going to do 2 inversions in different folders. So just in case you want to use a configuration for one pixel and try something different for the other. So we are going to do this in separate folders. So then this is just the first part. And as a summary, so we created atmospheres. From that, we created profiles through DeSIRe, so making synthesis. We made, let's say, more realistic the profiles, adding some degradation, in this case, in the sense of noise. And now we have that those profiles will be the input for doing the inversion and to try to check how a given configuration and the code behaves to infer the atmosphere that we use for the synthesis. Okay, so then is there any other question before I move to the inversion process itself? No? Okay, so
Carlos, so in this case, since you did the forward synthesis with DeSIRe, you basically get the profiles in a shape or in a form that you can immediately use for an inversion, right?
Yes.
But if you, in general, you have, once you have observations, you'll have to normalize them to some form of continuum.
Yes.
And
yes.
I'm not sure, are you going to address that, or is that useful?
Not today. This will be part of a future class, because there I would like to cover, like in SER, where we normalize the continuum, we interpolate, or we create a profile with a uniform spectral sampling, and then we create a grid file that is compatible with that. So I think in this case, I wanted to just work in the process of inverting, and then there's at least, I think, 2 classes more where I will work more on how to get ready from an observation.
Yes. But I think it's important for people to realize that there is some work involved in getting the profiles to the right units, if you will, or unitless representation.
Yes. So the idea is that here we are simplifying the process because we are not changing this value or other things, but in the future we need to define the grid file and check that the lines are the correct ones, or maybe add new ones depending on the spectral window. So yeah, it will require some process that I hope maybe in 2 classes I will show people how to do it. Okay, but thanks for the comment. Okay, so then we finish in the first folder. So now we go to folder 2. We have that. Let me just load. I will close this one to avoid mixing things. So the name is the same, but now we have also this one. Okay. And then just to keep things organized, I will go to run 2. Okay. So then in this folder, again, I copied everything. So atoms, grid files, abundances, so everything is the same, but we are going to change the ideal procedure and also our control file. Now I'm calling it inversion just to keep things separated. And here we are going to also make some changes. Okay, so then if you go to run, it says that we are going to start with the input -1 profile. Okay, so then if we go to the inversion control file, so here you have that the observed profiles now are the input. Before in the synthesis, they were the output. So we were using an atmosphere, and from there we were generating the profiles with the name that we use here. Now it's the opposite. So now we are going to use the profiles with an initial atmosphere, but the final result will be profiles and also an atmosphere that matches as much as possible the profiles that we observe. But the rest of the things are the same. So the only thing is that we were going to change some things related with inversion. In this case, we start with different number of cycles than 0. 0 is synthesis, and then values above 0 are inversion cycles. Okay, so what we are going to do first is, as before, we need an atmosphere. And that atmosphere is the one DeSIRe will use to change the location of the nodes and then try to adjust it as much as possible to generate a profile that is close to the one we observe. Okay, so then in this case, we did the synthesis with an HSRA atmosphere, but I thought it could be interesting to make it a bit more difficult to decode. So we are going to start with an atmosphere that is a FAL-C model. So it means that our temperature and the rest of parameters are different. So then the code needs to work a bit harder to get to a profile that are similar to the one we have before. Okay, so then one important thing is that if you remember, DeSIRe and SER, they use nodes that are locations in optical depth where the code will change the atmosphere. So imagine magnetic fields like this. So if you have node in the extrema, then it can change the value, and then you can have a line that goes like this or like this. Okay, but if you remember from the SER tutorials, you cannot assign any given number. It's related to the number of dimensions or or the number of optical depth points that you have. And I explained that at that time that there's a procedure that we created that is called nodes. So you can use it for checking for a given dimension of your atmosphere, how many nodes you can assign for any given parameter. So then in my case, I used the FAL-C atmosphere and I cut it from log tau 1 to log tau -7 with a step of 0.1. And this gives us an atmosphere of 81 points. So let me just quickly show it to you. So this is the atmosphere, and it starts in 1 and goes up to log tau -7, and it starts in the second row. So it's a total of 81 points. Okay. So then if you type nodes and 81 or then the variable that I define here, you will get this number. So it's telling us that with this exact atmosphere or this given specific configuration, we can assign nodes to any atmospheric parameters that has a depth certification with this configuration. So 1, 2, 3, 5, 6, 9. If you give 7, then the code will take 6. If you give 8, the code will take 9. I think will take the closest one from each side. So just be aware when you define an atmosphere that you should have a given number. So for example, nodes, let me see if this works. Yes, but if you just remove 1 point, then you cannot use you can only use 1, 2, or 80. So if you set 10 cycles and you are saying in each cycle you go 3, 5, 6, 7, it will not work because it will use 1 or 2. So then this is something a bit tricky, but it's something that it's how it works. So just be careful when defining the atmosphere, because just removing one row, it will just stop you to being able to choose a an interesting set of nodes. And as a reference, I put here different values. So if you want to cut it, you can just go nodes and type different numbers, but you can see that I already put here some reference. So with 85, you have even a larger set. And also with 91, you can also have a lot of possible configurations. Okay, but it means making the atmosphere a bit longer, and sometimes this could be good, but if you go too high, you will always have one node in the extrema, and then you are putting a node in a region where you probably will never have a spectral line that is sensitive to. So I mean, lockdown -8 or -9, we are not observing lines that are sensitive to those regions. So then it's not so advisable to go really -9 or -10. So maybe between -6.5 and -8, I think is the best way for the top boundary. Okay. So then, and yes, and for this example, we are going to create just one initial atmosphere. But the idea is that I will explain it in the next class, that it's good to start with different initial atmospheres, because if they are different, they are going to produce a profile that could be very close or very far to different pixels that you want to invert. So then it can make things easier for the code in different cases, and also will allow the code to cover wider spectrum of chi-square values and minima. So we will check how to do that. But in today's class, just to keep things simple, only one atmosphere. But next class we will check it. Okay. So then I read the original atmosphere, and sorry, and I also mentioned that somewhere. Yes. So the Falsi model has a microturbulence certification that is changing with height in a very nice way, producing very realistic profiles. But you don't want to have this as an initial value. Otherwise, you have to provide a lot of nodes for microturbulence. So then I think it's better to just have a fixed value in the microturbulence and then let the code to try maybe 2 or 3 nodes. So then I took the original Falsi model, I cut it for having the specific number of optical depth points, and I also removed the microturbulence. I set it to 0 because otherwise you will have a stratification that is complex, and then if you have one node, the code will just move up and down a very complex stratification, and this will make things harder for the code. Only temperature is the one that we should have always with a complex pattern, because it's how it is. But microturbulence, I recommend you to just keep it flat, any constant value, and then let the code move from there. Okay, so then the original Falsi model without microturbulence and cut it, I read it, and then I just add a constant value microturbulence, constant magnetic field, constant velocity, constant inclination, and constant azimuth. I think having everything in constant is the best thing for starting. And then I will save it with this name, that is in guess mode. Okay, you can have it any name, but the idea is that this name is the one that we are going to write here. Okay, so when we initialize the process, this atmosphere is the atmosphere the code will start from. From there, it will change it every time in every iteration based on the response functions that it will compute for the Stokes profiles. And from there, it will change it slightly until it gets to a solution, the best solution possible in the given number of cycles. Okay. So then let's see how it looks. So it will be atmosphere inversion 1. So it's this one. No, this is already the result. Sorry. It's here. This one. Okay. So simple. Temperature is the FAL model, and then everything is constant. Okay. So then with this atmosphere, we run the code. Okay. But before that, just check what things I set differently from the synthesis. And then some of them, we will cover them in detail in the next class. And some of them I will just quickly explain them today here. So we put 3 cycles because I think it's a reasonable number. Maybe for chromospheric lines, you may want to go to 4 or 5, but for this example, I think it's fine. All these parameters are the same. So to keep things simple and consistent with the synthesis, as I said, this is our initial atmosphere. This is also the same. And then I put here some weights. I will explain more or less what they mean, but the next class we are going to work on this in really detail and for a lot of time. So the idea is that the code will compute a chi-square value. And from there, it will check if a given change in the atmosphere was in the good direction or in the bad direction. And from there, it will change things in the same direction or not. But the idea is that the way the code computes the chi-square value, it depends on different things, and you can tune it a bit. So what we are saying here is that an error in Stokes V, for us, it's 5 times more important, or well, a few times more important than Stokes I. And then we are saying that the Stokes Q and U errors are also a bit more important than Stokes I. So we are telling the code, try to fit all the parameters, but try to fit a bit better, both Stokes Q, U, and V. And this is something that we usually do because the amplitude of those profiles is smaller than Stokes I. So if you want to have accurate results, you have to tell the code somehow that a small error in Stokes V is probably more important than a slightly larger error in Stokes I, simply because Stokes I goes from 0 to 1, while Stokes V is always going to go from 0 point something to 0 point something. So it's just a way of telling the code that we want more importance on the errors of Stokes V and Q and U. Okay, but we will check this in detail in the next class. Okay, so then we have nodes for temperature and for the rest of parameters. Here I just put it 2, 3, or 5. So 2, it will be in the extrema, then 3 in the extrema and in the middle, and then 5 separated equidistant in the atmosphere. So then the code will change the atmosphere temperature in the, for example, in the third cycle up to 5 different positions. Electron pressure, we don't usually embed it because it's related to the temperature. So then we always leave this as a blank in general. Then microturbulence 1 node, and then I go up to 3 in magnetic field strength and velocity, and then 2 inclination and azimuth 1. If you remember, we did the synthesis with a linear gradient, but I wanted to give the option of adding like a parabolic behavior to DeSIRe, because I think in general, this would be the starting inversion configuration I would use with any observation. I will start with something like this, and then depending on the results, I will add more complexity, or maybe I will reduce the freedom in a given parameter. But I think this is a balanced configuration that you can always use as default. And then from there, checking the results, you can go from something more complex or maybe something easier. Then I put this instruction here, 0.1. So if you put 0, the DeSIRe will always recompute the departure coefficients through calling RH. And this is the most accurate case, but it's also the slowest one. So if you put 0.1, we are telling somehow the code that only if temperature changes are very, very big, we should reevaluate the departure coefficients. But if not, we just continue. And I think this speeds up a bit the process without really not affecting the accuracy. But if you want to be in the safe side, just put 0. And then you know that always in every iteration, independently of how the different parameters change, you are reevaluating the departure coefficients. Okay. And then this is the same. Yes.
Carlos, does this value like 0.1 or whether it's 0.2 actually relates to how much percentage of difference the code is looking, or?
Yes.
Okay.
So I need to confirm with Basilio, but I think this was in percentage. So I think this 0.1 means 10%. So I think this means that if the temperature in a given cycle in any point has a difference larger than 10% from the previous one, then the code will reevaluate the departure coefficients. Otherwise, it will continue.
So
Okay.
it can be means more sped up. Like if I fix 0.5, that means it's just only if it is 50%, then
Yes.
it is. So okay. Yeah.
Yes, yes, yes. So you can play a bit, and if you go very high, like 10, then the code will not run the non-LTE computation, only just at the beginning or at the end, or sometimes just not run it at all. Okay.
Okay.
Yeah. So I think 0.1 is safe, but if you want at the beginning, just put 0, just check that everything looks fine, and then just start increasing a bit, maybe 0.1. I would say that is the top, but maybe between 0 and 0.1, it will also depend on the number of cycles. So if you have here like 8 cycles, then you can speed up a lot of things. But if it's like 2 or 3 cycles, then you may don't gain too much, because maybe you are just avoiding one call, because the code will always recompute the departure coefficients at the beginning and at the end. So if you have like 2 cycles, we are just removing 1. So,
yes, yeah.
so I think it depends. But if you want to be conservative, I think it's fine to start with 0 for a few pixels, and then after that, just change maybe to 0.1. Okay.
Okay. Yeah. Thanks.
Okay. Okay. So then I was saying that now everything is the same. So then we have, with that, we can run the inversion. This is where we are located. So I think I can do it. I will just show the figures, but just to show you how it. So this one, okay, and then so just to see, this is the inversion, and it's going to run, but you will see that inverting 1 pixel in non-LTE will take like 10 seconds or 20 seconds with, I think, 700 points or something like that in wavelength. So it's really fast. So I just wanted to show you that the code, it's fast. So you can do tests like if you were using DeSIRe. So don't feel that it's going to take like 1 hour or 2 hours or more. So inverting 1 pixel, it will be a matter of maybe 30 seconds or something like that.
And if you put in 9, does that mean 900% difference? Or
sorry, Ryan?
in the control file, in
Yes,
that
let me go back.
place,
Yes.
if you put in 9, does that mean that there needs to be a 900% difference?
Yes, I think, but I think about 5 or something like that. I think it's basically LTE. So not LTE. It's just that the code will assume that you don't want to call RH in any. I mean, you don't want to recompute departure coefficients in any point. So let's say it another way. So you can have a mode that is this above 10, where you basically work as DeSIRe. So you make things as fast as possible, but everything is in LTE. So then chromospheric lines are wrong. But I need to check with Basilio. Just let me note down this, and I will check next week.
I think maybe Ryan wants to ask what's happening if I fix it in between 1 to 10. Because it's written greater than 10 is LTE, so and 1 means 100%. So what does
I think
greater than 1 and less than 10 means?
Yes, no, I think it's percent. So I mean, if 9 will be 900% change.
Oh,
so
okay.
So I need to double check with Basilio. Just let me take note. But I think it's just that. So you have to really have a huge change to make the code recompute the departure coefficients. Does it make sense what I said?
I think so, yeah.
Yeah. So essentially, for me, the default will be this if you want to speed up things, and 0 if you want to just make the best from the inversions. I think, Han, do you want to say something? Oh, okay. Okay, so then the code finished the inversion, and as you saw, we were just discussing the threshold that I want to sit down with Basilio to check that is what I said. So it's already finished, so that's fine. So let's quickly check what we get from the inversion. So then we will have 5 elements. So the first one will be the inverted profile. Okay. For keeping things simple and similar as in the third case. So the name will be the name you use in the initial atmosphere. So remember that our atmosphere was named guess. Okay. And that name, we will add dash a value, and this value will be the cycle. So in this case, we have 3. So then we will have a profile that goes to guess dash 3. Okay, dot pair. So this will be the profile the code could get to obtain the best fit in respect to the input profiles. Okay. In general, so in the third case, we printed all the profiles, so guess dash 1, guess dash 2, and so on. But in this case, as the final profile is the only one that we guarantee that we are reevaluating the departure coefficients and we are giving it as the best possible, we are just saving by default the last one, because independently of the threshold that you provide, the last profile will be always reevaluating the departure coefficient, so it will be the most accurate one. But if you are doing tests with different cycles, and for example, you have threshold 0, so you know that in every cycle you are having the departure coefficients reevaluated and you want to compare, you can add in this final evaluation of profile, I think is, let me see here. So if you add 1 there, then you will have guess dash 1 dot pair, guess dash 2 dot pair, and guess dash 3 dot pair. So you will have all the profiles. But in general, we assume that most of the users will just want to check the final one. So by default, it's just writing the final one. But just changing here to 1, you can have all of them. Okay.
Carlos,
Yes.
I have a question. The non-LTE threshold value is for all the cycles. Can you set up different threshold for different cycles, or?
I don't know. I need to check with
Okay.
Basilio. So I need to check with Basilio. Yeah.
Okay.
Yeah, it's a good question. I don't know, but if the answer is no, I think I will just ask Basilio. We can do it like this, and I don't know, something like this, and then 0 again. I think this probably will be possible, but I don't know if it's implemented. So just let me ask Basilio.
Well, but in the non-LTE threshold line, not there, right?
Oh, sorry. Yes, yes, I was writing in the wrong.
Okay.
Yes, I mean here.
Yeah.
Here.
But it would certainly be very useful if you could do it that way.
Yeah. Okay. I will check with Basilio. If it's not implemented, then it's easy to implement, and we will do it. Okay. Yeah. Okay. But thanks for the question. I already noted down. So then ask Basilio threshold and then threshold per cycle. Okay. Okay. Thanks. So then just let me remove this just in case. Okay. So then we were saying we have the profile. Now we will have the atmosphere that produced that profile. So the name is also following the same convention. So guess, then dash, and then the number of cycles. So in this case, it will be guess dash 3. Okay. Although in this case, I think it's writing by default all the models. So I don't know if we may also change that. I think it's fine, but for now, I think what it's doing is not writing all the profiles, but writing all the models. So I don't know if we will change that. But the important thing is that the atmosphere related to the guess dash 3 dot pair is guess that 3 dash 3 dot mod. Okay. Then we have a file that is called inversion.chi, and here is where the information related to the chi-square will be stored. I don't know exactly what each parameter means, so I promise that I will have a class explaining what they mean, because it's related to chi-square, but DeSIRe, and this is heritage from SER, the way chi-square is computed is a bit elaborated, so I will try to at least write down how this is done and present it in 1 or 2 classes from now. But the important thing is that if you are doing tests with, for example, the same configuration, but imagine that you are starting with 3 different atmospheres. So then in that case, you can compare the chi-square values. If you change nodes, something like that, then it's different because the chi-square is dependent on the number of nodes and other things. But if you have 3 atmospheres, 3 initial atmospheres, and you want to check which one produce a better result. So then in that case, you can look for the value, I think it's the second one, the value that is lower. Then you can really say that with the same configuration, the value that is lowest is the one that produces the best fit. But with different configuration, it's really difficult to compare. You have to do it by hand, or maybe I convince Basilio to add a different column where something reasonable is written here, and it's easy to compare different configurations. Okay, but for now, just keep in mind that there's a file that contains information of the chi-square value, and I will try to explain it maybe in 2 classes from now. Okay. And then there's also a log file that maybe I can open here. Yeah, and it has some information related to the chi-square values, but also some perturbations and other things that done related with iteration and internal things of DeSIRe. So in general, this is probably for us, so you don't need to really look at it, but maybe if you're doing a test and something is, so the code is stopping or there's some convergence issue, probably here you will have a hint that you can send it to us. Okay. So then there's a last, okay, bye, Han. Okay, see you. So then there's a last thing that is insert. If you remember, we had an output that was a file that was with the name of the, so imagine in this case was guess-3.error. Now we are not outputting this file because we are discussing which is the best option to do it, because our impression is that the SER error or uncertainty is not the best for understanding how uncertainties are treated here. So we are probably thinking that we can make it in a different way. So then the idea is that in a few classes, maybe 2 or 3, I will show you how it's done, and then we will update the code for also produce as an output the uncertainty of the atmosphere that obtain the best result. So for now, we just assume that we are not providing it. We are computing it internally, but we will decide how we give it to you. And if you want to really know now how you can estimate uncertainties, just try to follow what we did in the SER course, or maybe I can give a class on that. That was basically using the inverse of the response function as an uncertainty estimation, because where the response function is high, the uncertainty should be low because the profiles are sensitive to changes in the atmosphere. And where the response function is very, very, very small, then your uncertainty is huge because any change in the atmosphere there will produce no impact on the Stokes profile. Okay. But for now, just keep in mind that we will give uncertainties and we are just discussing how is the best way of doing it. Okay. So we have done the inversion. We understand more or less the output. So now let's check if the results were good. We ran 3 cycles. The freedom was not, so the number of nodes was not so high. So let's see if the code was able to fit the profiles. And for that, we can compare 2 things. So the most important one is the profiles. You should compare your input profiles with the fitted ones, because you can do that all the time. But in this case, as we have the original atmosphere, because we are doing synthesis, we are also going to compare the atmosphere that we obtain with the original one. But in general, with observations, you don't have that information. So it's only something that we can do here. But I recommend you to try it because it will allow you to understand a bit more how the code behaves when you change some things or the things, because you can really check if the results are improving or not. Okay, so then let's read the profiles. So this is the input. Okay, so this is going to be our reference, and as before, we have the three spectral regions together. So I'm separating them to make the plots of the different profiles together. Sorry, separately. And then we are reading the result. These are, as I said, -3 is the profile that we obtain in the third cycle with atmosphere from the third cycle. We separate it again, and then we make the plot. Okay, so then we go here and we check. So red is the result from the inversion, that there's no noise. And then black is the original profiles that they have the noise. So then I would say that with the configuration we are using, the results, for at least for the photospheric lines, are great. For me, in particular, Stokes I and V, they are wonderful. Stokes Q and U, there are some differences, but in general, this I would say that is a really good fit if you are saying me that black is observations. So I think we are starting really well. Now let's see what happens with the 8498. So here we have that Stokes I, it looks again really well. So the photospheric lines are really, or I would say almost perfect. We have some difference here, but okay, let's say that we are starting the process. So I was expecting some difference, but it's still not so bad. And then Q and U, they are not good because it's noise. So you can see here the code is trying to fit this noise variation. So be careful when you have only noise. Maybe we should reduce the weight on Stokes Q and U just to avoid the code to try to fit these things. And then in the case of Stokes V, photospheric lines are great, and chromospheric lines are, well, yeah, more or less. So let's say that it's trying, but the amplitude is not as good, and then this variation is not the same. But I would say that it's fine. So I'm okay with that result as a starting point, and then the same for the calcium 8542. Wings are really good, so it's nice. The core is okay, it's not the best, but it's okay. Q and U are not good, so we should be aware that maybe changing the noise, the weights could be better if we are going to have most of the pixels with this behavior. So imagine quite some. Most of the pixels will be dominated in Q and U by noise, so maybe reducing the weight will help. And then again, Stokes V, really good for all the lines, and for the 8542, it's okay. The amplitude is a bit higher than the original one, and it's not making this variation, so maybe it's not the best result, but I would say that this is a good starting point. And now what I'm going to do, I'm going to show you the last figure in this case, and what I'm going to do is to compare the atmosphere, and we are going to have 3 plots. So sorry, three lines per plot. The first one will be the input atmosphere. That is, we know because we did the synthesis. The second one is just as a reference. I'm going to also plot the atmospheric parameters of the atmosphere that we use for starting. And this is because I want to show you that in general, DeSIRe, as happened with SER, behaves really well in the sense that if you start far from the solution, in general, the code can go very close to it. So I just want to show you that we are not starting with the same atmosphere or very close to it. It's just that the code in general can go close to the solution. And then the final is the solution. Okay, so let's open this plot and let's try to see how it looks. Okay, so black is the goal. Okay, the atmosphere that we use for the synthesis. Dots, or yeah, I think it's about dots, is the atmosphere we started from. And then red is the atmosphere that we get after the third cycle. Okay, so in temperature, and I think this is why the photospheric lines, they are so good. So we started with the dots, remember, here. And the red just moved from there and it's on top of the black line on most of the cases until log tau -4. That is very good. Here you can see that the atmosphere was complex because in fact it's deviating a lot from here, but there's still the code, at least in this area, it matched most of the black line. Then here we have deviations, and I cannot tell you right now if this is a problem of configuration or simply that the lines between log tau -5, -5.5, for this atmosphere, they are maybe not so sensitive. But at least we are from log tau -5 to log tau 0, we are basically matching this certification. Microturbulence is fine. Velocity, not so good. The fits were good, but it seems that here we have some large deviations. And again, this is maybe that we are not fitting so well the profiles, and also maybe some lack of sensitivity to velocity. But I think this is especially that the fits were not so good. And the same with magnetic field. So it's not doing so good here. Inclination is fine, and then azimuth is also fine. So I think we are seeing more or less what we saw before. Fits are in general good, but we saw some differences in the core of the line. So I probably think there is difference in magnetic field and velocity. Okay, so then we have already 1 hour. So then just to keep things simple, I also prepared that folder, this one. And here we are just going to repeat exactly the same process, but using the different, so the other profile that we generated with a very strong magnetic field. So then I will just not show you the procedure because it's the same as this one, just changing where here we have a 1, I change it to a 2, and then where I have here input 1 is input 2, but it's the same. So just let me show you that with the same configuration, but with a different atmosphere, the results are also good. So just let me go back. So then we start with the iron lines. Remember that they had really strong amplitude, and here you can see the code is really fitting the profiles, even after adding noise and starting from a different atmosphere. Then if we go to the chromospheric lines, Stokes V is great. I think this is really a perfect, almost perfect match.
Yeah.
Yes, yes. Then I think the code is trying to do something here with polarization signals, and maybe I don't know if this is affected. We will see later with the magnetic field, but this is an issue that we should be careful. So if you have this type of noisy profiles, don't try to push the weights here, because as you can see, the code is trying to do something, but it's fitting noise, and this is not good for in general. And then Stokes I is also very good, although here we see a small difference, but this, as we will see now, is essentially temperature, that we may need more nodes for obtaining a better fit, or a different type of weight configuration. But let's continue with the Stokes, with the 8542. And here again, it looks very nice. It's not as good as before. So just let me make some zoom. We have again that this complex variation that we have, it's there, but the amplitude is a bit larger. But again, I think this is really good. It's just that we have to say something. And again, Stokes I, very good, and just a minor error here. But for me, if you show me this from observations, I would say that's perfect. Okay, so then why it seems that the code is not getting really perfect? So again, we started from the dot line, and then the code is again with the red line is matching the dark line in almost all the cases. But then it seems that here it's not really on top, and then here it's not really on top. So I don't know if those slight variations that are not really exactly matching the input atmosphere could be the reason why the core is not exactly the same. But again, those errors are really small. Here again, I was giving more nodes than a line for the atmospheric parameters, just to let the code to know how it will behave. And it's doing like a parabolic behavior, but in general, it's matching the line most of the regions. And then I think these deviations are probably due to a lack of sensitivity of the chromospheric lines, maybe in octal -6. And the same with the magnetic field. Okay, so then at this point, I think I covered more or less what I wanted to say. Just let me, yes, I will read this. And then I will tell you what we will do next week. That is essentially play a bit with different things to learn how you can improve or degrade the results, because sometimes you can force the code to do something that you believe is better, and then everything collapses. But the important thing is that today I wanted to show you how you can run a non-NLTE inversion in less than 1 minute. It was completed. And I wanted to recommend you also to start always with something very simple, because the code is really, really versatile. So if you start with constant atmospheres and with not so many freedom, the code usually goes close to the profile, and usually in average, or in average, the results will be reasonable. And after that, maybe you need to fine tune, but just small things. But start simple, and you will see that the code will behave really, really well, as usually DeSIRe also does. Okay, so then I think I don't need to read this. It's just as a summary. So we set the synthesis with a HSRA atmosphere. We added noise, and then we inverted those profiles from a falsy atmosphere. And then the code was facing a different thermal part, so it needed to try to adjust it. It was also facing noise, that it was changing the profile, so the code cannot really know if those perturbations are actually profiles or noise. So then it's also a challenge. And this is what we usually have in observations. And for me, the results are really good. So I think I just wanted to show you that the process is relatively easy, and things work without really trying too many things at the beginning. And then the idea is that from that, we will move a bit to a more expert mode to just fine tune some things. And then I think you will be ready for inverting profiles. So I think this is going fast, but this will arrive later. So then before going back to the presentation and just covering the last part of the class, is there any question until this point?
I have a comment, Carlos.
Yes.
So in the inversions that you have shown now, as you have already shown, is the photospheric is quite well fit in the models,
yes.
And the chromosphere not so well.
Mm-hmm.
I wonder, or I have a guess, is that in your inversions you are using in any of these two lines, in 8498 and 8542, you are including several photospheric lines, while you have only one chromospheric lines. So my question is, or my guess is, that if you simultaneously invert 8498 and 8542, including the photospheric lines that you are including, probably you are going to start to constrain better the chromosphere as well, because you are in one case you are having 3 photospheric lines and 1 chromospheric line, and if you include these 2 chromospheric lines, you are going to have a better constraint.
Sorry,
So
maybe I'm inverting all the lines together. So is this what
no, you are inverting okay, so you are inverting a full profile, what is including 8542 and 84.
Yes.
Okay. I
yes,
thought you were splitting and doing the inversion independently for these lines. Okay.
So the three spectral windows are including together, and I'm inverting together everything. Yeah, I think so otherwise you will not have the chromosphere like we have.
Okay. Okay. So, but even in this case, you have a large number of photospheric lines, right? You have like 6 lines. Yeah. Okay.
Yes.
No, it's very.
Yes.
I think
yes.
the results are very
yes.
good.
So the idea is that in the next week I will improve a bit more this result. I
Yeah,
was
yeah,
trying
yeah.
today, and we can improve it with a different configuration, not in the terms of nodes, not in the terms of lines, so just other things that I will show you in the next class. But the idea is that I think this is very promising configuration. So probably if we have errors, could be some of some things that I will show you how to change in the next class, or because maybe for a given atmosphere the response function has shifted a bit and the lines are maybe not sensitive in those layers. But I think this is really a good configuration and is close or the same that we will have with the first observation from the KISS WISP. Okay, so
Okay.
yeah, okay,
Really nice.
but still we will improve it a bit in the next
Yeah,
class.
yeah, yeah, yeah.
So okay, so then any additional question?
I just wanted to quickly ask, did you check the model and how it compares to the original for cycle 2? Because in the first case with the velocity, it kind of, I had a suspicion that
maybe
2 nodes would be better.
And
I wonder if the fact that it's missing is just a consequence of it just being too many nodes. If you know what I mean.
Yeah, it could be. So you mean that maybe model 2 in this case was aligned, and then in model 3 it decided to move away? Yeah,
I think so.
I think yes. Yeah, I will check it. But but the idea is that in general, I think the atmosphere will be a bit more complex. So I think velocity and magnetic field, if you have enough wavelength points, I think 2 or maybe 3 is probably the minimum if you are having chromospheric and photospheric lines together.
Yes,
so,
I mean,
so I just wanted to just keep something that you can use as default. But in this case, as we are using linear as an input, probably the code was not maybe made a mistake. But I think if you are having observations with enough spectral sampling, probably 3 should be, and all this optical depth coverage, probably 3 should be something that you should start from always, and then maybe move to 5 or even 9 if you have complex velocity patterns. Maybe Alberto want to say something?
No,
Ryan?
no, that okay. I understand Brian's comment, but it's taking advantage of the knowledge we have of the atmosphere, right? Like, oh, I know it's a linear gradient, so if I go to a cycle,
yes.
But generally, unfortunately, we don't know the atmosphere.
Yes. But at least I think my impression is that this is probably the responsible and this one of not so good agreement on Stokes I and Stokes B also. So probably this difference. But this particular case, I was testing today one option that we added in this side, and it's working better with that option. So in the next class, we will focus on this one without changing the nodes configuration and other things, how we can improve a bit more this, because of the fact that we are combining chromospheric and photospheric lines. And this is something that we have not done routinely, at least with DeSIRe in the past. And we added new options to maybe improve this new challenge. So in the next class, I will show you how we can improve this even with this simple configuration. Okay. So any additional question? Ryan,
so
Alberto,
does this mean,
yes.
Carlos, does this mean that we should have some sensible selection of spectral lines for inversion rather than just throw everything what we have and invert?
Yes.
Okay.
So imagine that you have a very broad window with like 20 lines. I think you may add them, but maybe some of the lines are really almost the same between them. So maybe you just need to have 5 or 6 that are complementary. So one is more sensitive to temperature, the other is more sensitive to magnetic field and things like that. And I think we are already doing it here. So choosing the 2 calcium lines plus the iron lines in the visible, we are already doing this complementary configuration. Okay. Yeah. Okay. So then, Nancy, you're missing. Do you want to add a question? We have already covered Ryan, Alberto, and Dato.
No.
Okay.
No
Okay.
question.
Okay. Okay.
Yeah.
Okay. Sangeeta, I think also no question.
No questions.
Okay. 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 So then let's go back to the presentation. Just very quickly, because today I think it went a bit longer than usual. So try to examine all the files, the input files for the synthesis, and then the synthesis, and then the inversion. Try to understand the inversion process, and always keep in mind that the first folder where we synthesize the profiles is something that we don't usually do, because we get the profiles from the observation, but just try to get an idea of how we did it. This is what I said. So we will have the data soon from a lot of missions, including the current facilities. And then, as I said, I'm not going to really force the code to match or to obtain the best, or the atmosphere that we use as an input. But there are some techniques that we will learn in the next class to better match the profiles. We will see that this is not translated exactly on a better atmosphere. It could be because of different reasons, but I will show you things for obtaining better fits of the profiles. That is our measurement of how accurate the process is when we only have observations. And this we will do it in the next week. So I will try to teach you how to get ready to get the best from observations, even if you don't know what is the atmosphere that is behind. Okay. And then if you have time and you want to have fun, I think you can add more complex atmosphere as an input, synthesize the profiles, add noise, and then just repeat the process and play a bit with the code to just see how it behaves. And then in the next class, I think I wanted to cover 2 topics. I'm not sure if we will cover them, but at least I will put it here. So the first one is, as I said, improving the configuration to get better fits. And then if we have time, we will learn how to prepare everything to just do a synthesis with a snapshot from Bifrost, because then we will have profiles with magnetic field, with gradients, without gradients, higher temperature, lower temperature, and then eventually we will invert the full map. And there we still have the atmosphere, so we can really check if the results are good at all layers or somewhere, but we will have much more different scenarios. But I think we are not going to be able to cover in the next class, because I want to go slow in the first part, because it's new, completely new con respect to what we did in CER. But if we don't have the time, then we will do it in the next class after that. Okay, so then I want to see you in 2 weeks. So I hope you will be ready to meet again. And then, is there any last question? No? Okay, so then enjoy the weekend. And thanks a lot for joining us today. Okay.
Thank you, Carlos.
Bye.
Bye.
Thank you.
very much.
Bye-bye.
Thank you. Bye.
See you.